Hi, Assalamualaikum, and a very good day. I bid to everyone. I hope you are doing okay. And First and foremost, I would like to congratulate everyone for being committed to our online classes. So far, we had um, the first class run very beautifully, I would say, from the response that I received from you towards the video that I posted on the YouTube, as well as on your comments on the Padlets, as well as your active participation in a WhatsApp chat discussion. So congratulations everyone. I hope you and me, can keep the same momentum throughout this semester. So we can do this together, inshallah. So whether the PKP will be lifted or not by 20th April, we are still going to have online classes just like this. So bear with me, bear with the system for a while, and hopefully we can deliver these online classes more effectively from time to time. Why did I say that? Because I realized that my first video, the screen that I shared with you was quite small, as in the lecture note that I projected in the first video was quite not optimal, I would say. So I received that comment from my friend too. So I think for a better and clearer view of my presentation now, I am changing the screen size. So I hope this works well to both of us. Now, speaking of the syllabus that we are going to discuss today. So again, I would like to go through the carbonyl complexes. I'm sure some of you might have had a bit of confusion on this concept. But before we move further on how carbonyl complexes can be formed, we need to understand the properties of carbonyl complexes, or the carbonyl as a coordinated ligand, carbon monoxide as a coordinated ligand first. Now look at these notes. I'm sure you all have these with you. For carbonyl complexes, they are called pi acid ligand or pi acceptor. So we already knew what acid means for this kind of ligand. We we are referring to the Lewis definition of acid, where this ligand is actually able to accept electrons in. But that is the acidic part of the ligand. But why we are putting pi there? Why it is called pi acid ligand? So this is something that I have missed to discuss earlier, and I intentionally postpone it to this video because I did not want you to get confused. Now, later we are going to see the mechanisms on how these complexes are formed. So, in that definition, I'll be using the term like sigma orbitals or pi orbitals. So we are actually referring to the sigma and pi orbitals of our molecular compounds, which is carbonyl ligand or carbon monoxide. So remember, the other day we have gone through this and we have learned uh, on how to construct molecular orbitals of carbon monoxide. So this is well known. I hope so. So from this diagram, we understood that the HOMO for your carbonyl is sigma antibonding, and the LUMO for your carbonyl is pi antibonding. So we have non-bonding electrons here from sigma orbitals. We have bonding sigma orbitals here, and we have bonding pi orbitals here, and we have bonding sigma antibonding sigma antibonding orbitals here. Now you have to understand this table. Only then you will understand what we are going to learn today on the compensation mechanism. So ready? Now we are going to learn how metal complexes are formed, specifically for carbonyl complexes. So as I said, for a metal complex to be formed, you must have an organic compound which is called ligand. Ligand must have donor atoms, only then they can donate the electrons to your metal. So in this case, your ligand is carbon monoxide, and your metals can be any metals. Carbon monoxide is a good ligand because it can form metal complexes with many transition metals. So I put it as M here. Now you have to recall again the molecular orbitals that I have shown you slightly earlier. So from that diagram, we understood that there are LUMO, there are HOMO. So these are the things that we are going to discuss in details here. So there are two steps that need to be taken in order to produce carbonyl complexes. The first one, the field sigma orbital on carbon. Okay, I would like to highlight here the field sigma orbitals on carbon from carbon monoxide will be overlapping with the sigma orbitals of your metal. So since the overlapping is happening between two sigma orbitals, they are going to form a sigma bond. So the first step of forming your carbonyl complexes is actually the formation of sigma bond between sigma orbitals of your carbon from carbon monoxide with the sigma orbitals of your metals. Okay, that's the first step. The second step is, before you go to the second step, now once the sigma bond is formed, we understood that the electrons will be flowing from carbon to metals. There will be a point where there is an excessive number of electrons coming in into the metals. So since your metal is electropositive by nature, so it will tend to reduce this charge. How? By giving back the electrons to the ligand. But this can only happen if your ligand has empty orbitals. So whether or not it has empty orbitals, we have to see the second step. So in the second step, a field d pi orbitals or hybrid molecular orbitals on the metals overlaps with an empty pi orbitals on the carbon monoxide. So now the first step, just now we form a sigma bond between sigma orbitals of your carbonyl and sigma orbitals of your metal. Hence, there is a formation of sigma bond. In the second step, there is an overlapping of molecular orbitals between hybrid pi molecular orbitals on the metal with an empty orbital on the carbon monoxide. So we have formed the first static bond, and now we are forming the second one. So this is called pi bond. Why is pi bond? Because the overlapping is happening between field d pi orbitals of your metal with an empty pi orbitals on the CO. Okay, so forming the dative bond. Now CO in this case acts as the pi electron acceptor. So that's why we call it pi acid ligand. Remember just now I told you that for the metal to be able to reduce the charge, they must be pushing the electrons back to the ligand. But this can only happen if your ligands have available empty orbitals. So in this case, we have carbonyl. So carbonyl does have the empty orbitals. That's why we call it pi acid ligand. Meaning, according to Lewis, it can accept electrons. So they are pi electrons acceptor. So that's why in this case, there is a possibility for the carbon monoxide or carbonyl to accept back the number of electrons given by metal. So that's why it's called pi acid ligand. I hope you are clear on that particular concept. So from this diagram, we can see that there is an overlapping between pi orbitals of metals with empty pi orbitals of carbonyl, forming a second dative bond, which is your pi bond. Now, the flow of electrons from carbonyl ligand to metal, forming sigma bond in the first step, will make the carbonyl slightly positive. So this is basic. When you are giving away your electrons, you are becoming more positive. When you are donating your electrons, you're becoming more positive. And will be enhancing the acceptor strength of the pi orbitals. So because in order to accept more electrons later, you have to be slightly positive, because electrons that will be coming in are definitely negatively charged. So you must be slightly positive. Only then you will have a greater tendency to accept the electrons in. Yeah. So the drift of electrons from carbonyl ligand to the metal in the sigma bond tends to make the carbonyl slightly positive. That's why I said just now. So it will enhance the acceptor strength of the pi orbitals. But at the same time, the flow of electrons from metal into the carbonyl will make your carbonyl slightly negative. So this will increase its basicity via the sigma orbital. So increased basicity means we are referring to the definitions of Lewis. So Lewis base must be one that can give electrons. So electrons giver. So your carbonyl will give the electrons back to the metal. Metal will give back the electrons to the carbonyl. So this is called back bonding. Okay. So the effect of sigma bond formation in the first step will strengthen the formation of pi bond in the second. Yeah. So this kind of bonding mechanism is called synergic. So the conclusion that we can make here is that the more sigma donation that we can make from the ligand or by the carbonyl, the stronger the pi back bonding interaction from the metal to the CO. Okay, so far, what have we learned? We learned the formation of carbonyl complex. There are two steps. One is the formation of sigma bond. This can happen through the overlapping of sigma orbitals of your carbon from carbonyl with the sigma orbitals of your metal. Second is the formation of pi bond. So this can be seen through the overlapping of your pi d orbitals of your metals with the empty pi orbitals of your ligand. So forming second dative bond, which is called pi bond. Okay, and then we have learned about back bonding, and then we have learned also about synergic bonding. Okay, I hope you are clear on that. If you have anything that you don't understand, do not hesitate to ask me later in the WhatsApp chat or on the Padlet. Okay. Now, the second part of this now we are going to learn binary carbonyl complexes. I'm sure we all remember this because I repeatedly reiterated this in class. So I'm sure it has stuck in your mind then. But of course, there is no harm in recalling and refreshing. Now, carbonyl complexes, we call it binary when only two entity is in the complex. For example, we have one type of metal and one type of ligand. So it is called binary. It doesn't have to be a complex to be a binary compound. The normal binary compound like nitrogen monoxide, that is binary compound. It has nitrogen, it has oxygen. So regardless the number of nitrogen and oxygen in that formation as long as you have one nitrogen, and as long as you have nitrogen and oxygen, it is called binary. I hope it is clear. And the second term is homolactic. Homolactic means you only have one kind of ligand in the metal complex. So the opposite of homolactic is heterolactic. So I hope you can tell me what heterolactic means. So how many questions you have so far? So for you to know and for you to count and find the answers. Later we are going to discuss this. Okay. Find what is the meaning of heterolactic and please give me a specific example. That is one. It's best if you can get different examples from 74 of you. Is that possible? Okay. Now we know what is binary, we know what is homolactic. Now we are going to learn how to synthesize metal carbonyls. So the first step is we can have the metal carbonyl by having direct reaction between metal and carbonyl. Only two metals can have this kind of reaction. First, iron, and second is nickel. So under very mild conditions, so you're gonna get your iron, CO5, we call it penta carbonyl, and also nickel, CO4, we call it nickel tetracarbonyl. So both compounds are very toxic because they can easily release carbon monoxide. So why it is dangerous? Why it is harmful? Can you tell me why CO gas is not good to human? That's another question for you to answer. So the first type is direct reaction between metal and carbon monoxide, and second is reductive carbonylation. So this reductive carbonylation, when I say carbonylation, that means you are passing through carbon monoxide gas. So we can use two kinds of compound, metal halide as well as metal oxide. So this example of metal halide, chromium trichloride. Okay, you react with aluminium and then carbon monoxide, you're gonna get your carbonyl molecules here. So this is called carbonyl complex. Okay, so this is your carbonyl complex. I'm sorry, the drawing is quite bad because I don't have mouse here, but this is your carbonyl complex. So this is called reductive carbonylation. Why so? Why we call it reductive carbonylation? Why can't we just call it carbonylation? So this is another question that you have to answer. So we can discuss later in WhatsApp chat. Okay. So first we use metal halide CrCl3. Second we are using metal oxides Re2O7. I think I did ask this question in your class. If you remember, what is Re? Can you give me? This is not an important question and not something that we're going to discuss later, but something to for you to find out also. Okay. So you see from metal oxide, XO, MO, and then carbonylate, you are going to get your carbonyl complexes. Okay. The second term that we are going to learn, higher nuclearity carbonyls. Nuclearity, as I said earlier, meaning we have indicates the number of metals that we have in any given complex. So if we have one metal in one complex, it is called mononuclear. So that is nuclearity. If you have two, it is dinuclear, then three trinuclear, and you have many metals, you're going to be called it's going to be called polynuclear metal complexes. So we can get higher nuclearity carbonyls from lower nuclearity carbonyls. So how is that possible? So your OS, again, what is OS? If you remember, for you to know, for you to find out, we have discussed this. This can be done through thermolysis. When I say thermo, means we are using the thermal. Thermal meaning we are using certain heat here. So that's why this symbol is used. So you are going to get from one metal, you're going to have three metals, so trinuclear. And secondly, you are going to get higher nuclearity of carbonyls through photochemical bond cleavage. So photochemical bond cleavage. So that's why we are using this symbol. So from one iron, now it has become two iron or dinuclear carbonyl complex. So I hope it is clear that the second part of the lecture, we learn ways of synthesizing your metal carbonyls. Okay, it can be through direct reactions of metal with carbonyl or through reductive combination. Okay, that's all for now. I think it's quite a long lecture. See you in the WhatsApp group. Thank you very much. Assalamualaikum. And don't forget to like, comment, share, and subscribe. Thank you very much.